Okay, so let's get to the week 7 code. As usual, we're going to go to our usual directory. We want ggplot. We're going to use the class library, which has a lot of these things like discriminant analysis in. We're also going to use ISLR, which is the free textbook, as we use some of their data sets. And we're going to use my little my helper function, which helps the one I wrote to help calculate things like accuracy, precision, recall, etc. So we're going to do exactly what I'll skip over this because we're going to do exactly what we did last week. We have this auto data set, and we have this indicator. We created this indicator variable. Let's just view it to remind you. And it's a 0 if it's got less fuel economy than average, and a 1 if it's greater than average. And we have some information about the car and the car engine. And if you recall from last week, because fuel economy is pretty directly related to these variables, we actually got pretty good prediction trying to calculate whether we had a 1 or a 0, whether we were more or less kind of higher or lower fuel economy than average. Okay, so let's just mass and class. You can do a help on these. These basically are these include a lot of like classification and prediction functions. So let's first just see how many rows we have in our data set. We're going to sample half of those. This is just what we did last week. We're going to create a training sample. So we're just basically going to randomly select half our items, sampling without replacement. So these are the items that we've selected. And we're going to now do LDA, linear discriminant analysis. Now notice LDA looks a lot like regression. We've got our dependent variable to the left, which is what we're trying to predict, and the dot means we include all the other variables in the data set. So it's except with the fact we use LDA, it's pretty much all the other data sets. And here, we could have actually done auto 3 and then put in brackets, just train comma, to have all the training rows, but we're using subset equals train. Multiple ways to do this, as always within R. Now, weirdly, with this function, just giving the function name has most of the output. The summary doesn't give us very much. So the first thing we get is we get the prior probabilities of being in each class. So we said, it was supposed to be even, but it wasn't quite even. So we have 52% less than average, 48% greater than average. Now, importantly, it tells us the group means for each of these classes. So this is where we actually get some interpretation. So the less fuel efficient cars have more horsepower, more weight, more displacement, a little bit less acceleration, and more cylinders. And then the more fuel efficient cars, less horsepower, less weight, less displacement. They're smaller compact cars. It's kind of common sense. And then this gives us, the discrimination between the two classes. And if anything, this doesn't give us as much useful information as we would actually, get from the group means. So the group means here is actually possibly the most important thing, because these guys are kind of traded off against each other. So this is like the really important stuff. Sorry, I shouldn't be creating the videos late on a Sunday. I promise to stop yawning. Okay, so the discriminant analysis actually has that plot I showed you before. It's got something similar, and we can see the distribution for group 0 and group 1. Now you see here, group 0, everything to the left of this line is correctly classified, and everything to the right is not correctly classified. For group 1, everything to the right of the line is correctly classified, and everything to the left is not. So this is just the difference from the discriminant line going between the two classes. And group 0 is to the left of the, should be to the left of the line, and group 1 to the right of the line. But of course, in the real world, we can't classify perfectly, so we have a few. This one was classified, was predicted as group 0, but it's obviously group 1. Now, what we can do is, now we've got our training set, what we're going to do is we're going to test this model on test set. So again, we use the predict function as we did with regression. We pass our model, in this case LDA.auto, and then we pass our test data, which here is just minus train. And again, I guess I could have used subset here, but this is just, we're using the order data set and everything not in the training set. And so we actually get the predictions. Now what LDA gives you is, where do we go? It gives you 3 pieces of information. It actually gives you the posterior probabilities. So we could say that item 1 has a 99% chance of being in 0 and a less than 1% chance being in class 1. So we classify this as group 0, we classify this as group 0, etc. We classify this as group 1. But it also gives the actual class prediction. So if the probability of 0 is greater than half, then it will be a 0. And if the probability of 1 is greater than a half, then it will be a 1. So let's just go my little class eval function. What are we doing? Well, this is just taking on the test data. This is taking the actual variables. This is taking the actual y's. There we go. And this is taking the predictions, the y hats. And the third little parameter of my function, remember, this was just, this is just what is the positive class, and in this case is 1. So here we are, we have an accuracy overall about 88%, similar to what we got last week. Precision of 0.86, recall of 0.91, and specificity of 0.84. And we can actually do the table command again, just getting the actual y values here and the class y values here. And you can actually see we've got the classes on the rows, the predictions on the rows, and the actual classes on the columns. And we can actually see, 0, 0, 79, 1, 0, 93. So the ones on the diagonal are the ones that have been classified correctly. Okay, so just remove that. Okay, and as I said, when you take a sample, you're going to get a slightly a 50% test and 50% training. You're going to get something slightly different each time. So let's do as we did last week. Let's run it 100 times. We start off with an accuracy of 0. We do exactly what we've just done. But each time, rather than just reporting the accuracy, we add the accuracy to this overall accuracy variable. So we do this 100 times, and then we divide by 100. So again, this is utilizing the for loop. We're just going through 100 times with going I is 1, I is 2, I is 3. And all this is doing is just allowing us to get a little bit more accuracy. And then after our 100 experimental runs, our accuracy is 88.9%. So it's almost identical to last time. So now let's do the same for quadratic discriminant analysis. So again, we're going to make our training data. It's the same data set, so we don't have to calculate n again or n sample. And these are our training items. Now notice, rather than QDA, we just say LDA. Exactly the same before, except the Q replaces the L. And let's just see what results we get. And we got the prior probabilities. We've got the group means. Though again, the equation is much more complicated now, so it doesn't even bother showing this. You can see it's very similar as before. That the the less fuel efficient class has more horsepower, more weight, more displacement, and more cylinders. And we can do our predictions. Okay, so let's try and do the table prediction here. And we see here, for example, remember the rows are the predictions and the columns are the actuals. So we can see that, yes, it's a pretty good prediction. The specificity, the zeros, is probably a little bit less accurate than, you see that's actually 86% than the actual recall here. We see quite a few zeros have been classified as 1. But again, the average for most of these algorithms on this data set is around 88%. So let's try and do 100 runs as we did previously. And again, this is exactly what we did before. We run quadratic discriminant analysis. We make our predictions. We use our class eval function. Then we keep adding the accuracy and divide by the number of runs. And we get 89.3%. What was my LDA accuracy? Let's just see. Remind myself. So we got a slight, very minor bump. It's almost, could be chance from quadratic discriminant analysis. Okay, so the next thing we're going to do is we're actually going to play around with a little bit of cross-validation. And what we need, I've got a few extra packages. The most important one is the Carre package, because this allows us to implement cross-validation. So let's just kind of remind, we're talking about cross-validation. Okay, so let's clear the canvas. And so we've got our X's here. So this is all our independent variables. And we've got our Y here. And we're going to make some predictions. Y hat. And let's just say we've got 10 here. So we do 4, 4. Okay. So this should be like 10 equal strips. But, I wasn't employed for my drawing ability. Okay, so we have our data here. This is, so we have a load of like prediction data. So this could be like the horsepower and stuff for the cars. It could be what was sort of the scores for different films and music for the consumer data set. And we have some sort of Y here. So we might have our Y's there. Now, let's not worry too much about the Y's. So what we're going to do here is we split our data set into 10. So the first run, we actually have this as our test. And the remainder of our data set is the training. So we build our model on this training data set. And we basically run it on the test data set and then create what we call out of sample predictions. And we already have all the Y's here. And then we can compare them. And then we do the same again. So this time, this is the test. And then the other 9/10 of the data are the training. So everything else is training. And again, on the remaining test data, we make our predictions. And we compare them with our Y hats. So eventually, for every item, we have a Y and a Y hat. And then we can use all the measures we've talked about thus far. We can calculate things like the recall, precision, specificity, and accuracy. So the idea is every item is going to be in one of these 10 test data sets. And we just literally go through. So first we have this is my test, then this is my test, then this is my test, and each time we're using the other 9/10 of the data set as training. And this is basically called k-fold validation, where in this case k equals 10. So the idea here, the advantage of what we would be over what we were doing before, is that we're building our models with 9/10 of the data each time. So we have more training data to build our model. We aren't wasting as much of the data. We could go to a kind of complete extremes, and we've got something called L leave one out cross validation, and say we had like 10,000 items. Each run we'll train on 9,999, and then we will test on the remaining one. But you can imagine with a large data set, that's actually going to doing this like 10,000 times. It's going to take a lot of time. So this is kind of almost an in-between. The bigger the K, the more accuracy we get, but the longer it takes to run. So let's just see how we implement it in Caret. And in Caret, what we do is we actually define something called a train control. And we say we're going to use cross validation. We're going to have 10-fold cross validation. This basically does the cross validation for us. Now, we're going to run the model using Caret, and Caret has a train function to do all the training for us. And the only thing we had to do is the miles per gallon. We had a 0 or 1. We need to make sure this is a factor. And this is just purely because Caret, if you're doing class, the dependent variable needs to be a factor. So again, we use the train function. The dependent variable is miles per gallon as before. And we basically, the formula as with our individual functions. We set our data. And we also have we pass our train control. We tell it which method we're going to use. This time we're going to do logistic regression. And any parameters to that method. So we use GLM, and remember when we used GLM, we had to pass the family parameter and call it binomial. So we basically build our model, we do the train control, and then we get the results. And this time we actually get the level of accuracy, and then the kappa is just the accuracy, but accounting for random chance. So say, for example, we had a data set with 99% zeros and 1% ones. We just put 0 every time. Then we're going to get very high accuracy. But just by, we would actually probably be able to get it with just a naive algorithm. What kappa does is it just subtracts the random. If you were guessing randomly, it basically it subtracts the random agreement from the accuracy. So it's just a slightly altered accuracy, and we get the standard deviation of both the accuracy and the kappa. So we've got an accuracy of 0.888, which was in the area we're looking for, and kappa is a little bit lower. Now we're going to do exactly the same as the linear discriminant analysis. We've got the miles per gallon, we've got our data, we've got our train control. Let's just see what we get. We get, it's very, very little. We get slightly higher accuracy for our linear discriminant analysis and slightly higher kappa. Okay, so let's just have a slightly different data set. This is a credit default data set. So let's just have a look at it. And this is basically the credit data set. We've got the limit, we've got the gender, we've got education, marriage, age, and then we have a lot of extra information. So we're just going to do a simplified version of the credit data set. And what I'm doing here with this function is basically some of these guys are factors. Some of these, like sex, education, and marriage, are categorical variables. So what I'm doing is the lapply function is saying we're going to convert each of these to a factor. This is called list apply. And each of these individual columns I'm going to actually make into a factor column. And we have the string credit default. And again, we have these things like, I think this must be here some measure of whether they've paid their bills or not, or whether they're late. This is the amount of the bills, and this is the amount they've kind of paid in different areas. So we're going to use all this information to predict whether they're going to default or not. So let's run the logistic regression. The y is a dependent variable. These are all the things we're going to use to predict it. We're going to use the same control as last time, exactly the same code. And this is a bigger data set, so it's actually going to take us a little bit longer. If it seems like it's going to take too long, I'll just stop the video for a second to let it run. Okay, and so we get an accuracy of 81% and a kappa of 0.2881. Now, why is this kappa much lower? Well, this is a much harder problem. You know, the car one was an easy problem. Big, gas-guzzling, heavy vehicles tend to be less fuel efficient. This one is actually predicting consumer behavior, which is a harder task. Now, let's do the same for linear discriminant analysis. And see how that goes. And again, we get almost these techniques, these simple techniques work very similar. So linear discriminant analysis works a little bit better than logistic regression. Okay, just to summarize what we've done in this class. We've introduced linear discriminant analysis and some variants such as quadratic discriminant analysis. We've talked about, and then we've ran them in a very similar way to what we did last week with the k nearest neighbors and logistic regression. We went through a little bit of the theory of linear discriminant analysis, not too much. I left most of the math to the textbook, but you do need to know about these ideas of posteriors, probabilities, prior probabilities, how it kind of, how discriminant analysis utilizes kind of Bayes' rule, but none of the actual real math you have to know about that. And then we kind of implemented it in R. And then finally, we talked a little bit about cross-validation. And we're getting a little bit more sophisticated than taking our 50% training and 50% test. So we introduced this library for Carre that allows us to run this k-fold cross-validation with our methods to give a good idea about how accurate our models are and how accurate our results